Hey everyone, my name's Alex McDonough. I got my PhD a couple months ago in pure math, and I'm a big fan of 3 Blue 1 Brown, so I'm excited to be part of this Summer of Math expedition. The idea of this talk is I'm going to be sharing with you the introduction for me into research mathematics. And that was through chip firing, the Sandpile Group, and Rotor-Routing. And I'm mostly aiming this talk towards undergrads who have done some math or interested in undergrad math classes, but haven't quite got to the research point yet. But I do think that anybody hopefully can get something out of this. Not a lot of people have studied this topic. And even those that do, there's different perspectives to look at it. So I hope I can bring something a little bit different.
For this video, we will be working with graphs. A graph is a collection of points called vertices or nodes, as well as a collection of edges which connect some pairs of vertices. Here we have a graph with 4 vertices and 5 edges. For now, we're going to ignore the edges and assign an integral number of poker chips to each vertex, where negative det chips are allowed, but not fractional chips. Such an assignment is called a chip configuration. If we are given 2 chip configurations on the same graph, we can get a new chip configuration through pointwise addition. In fact, this pointwise addition operation gives the set of chip configurations a group structure. Here's the definition of a group if you'd like to pause and prove that these conditions are satisfied. The group of chip configurations under pointwise addition on a graph G is called the group of divisors of G and is denoted div G. I'm not going to get in the origin of this name, but it comes from algebraic geometry. Div G depends only on the vertices of our graph. Things get more interesting when we can fire chips across edges. When a vertex fires, it sends 1 chip to each of its neighbors. For this talk, any vertex is allowed to fire, even if it has a negative chip count. Notice that the ordering of firings is irrelevant for the resulting configuration. Also, if we fire every vertex, we get back to the configuration we started with. We say that chip configurations are firing equivalent if we can get from one to the other through some sequence of firings. This definition motivates a natural question. Which chip configurations are firing equivalent to a given chip configuration? See if you can think of a chip configuration that is definitely not equivalent to the one on the left. The simplest answer I can think of is any configuration with a different total number of chips. Firings cannot create or destroy chips, they can only rearrange them. So let's make things a little bit trickier. Instead of working with all configurations, we will only work with configurations with 0 total chips. These are called divisors of degree 0, written div 0 of G. Here are some exercises I encourage you to try if you want to get a little more practice with this material. Now it's time to introduce the star of the show, a group that has been rediscovered many times in many contexts and has more names than a piece of paper with 6 names on it. It's been called the critical group, graph Jacobian, graph Picard group, group of components, group of bicycles, and Laplacian co-kernel, but we will call it the Sandpile group. Every graph G has an associated Sandpile group, S of G. The Sandpile group of G is the quotient of div 0 of G by the firing equivalence relation. This means that the elements of S of G are the sets of firing equivalent chip configurations with 0 total chips. For example, X and Y are 2 elements of S of G. If we want to add 2 elements of S of G, we can choose any representative from each of the 2 classes and add them pointwise. In this example, X plus Y equals Y, while Y plus Y gives a new element. It's worth pausing to think about why this addition is well defined, and why this means that the Sandpile group is in fact a group. By this point, you've patiently listened to a lot of definitions, so I think you deserve to see why the Sandpile group is so special. For any connected graph G, the size of S of G is always a finite number. For the graph we've been working with, this group contains 8 elements. On the left, I've given a representative for each. This number corresponds exactly to the number of spanning trees of G, which are maximal sets of edges with no cycles. No matter what graph we work with, this amazing equality will always hold, and there are even generalizations to weighted or directed graphs. This is due to a beautiful theorem from the late 1800s called Kirchhoff's matrix tree theorem. This theorem is actually from almost a century before the Sandpile group was named, and is typically used as a formula for calculating the number of spanning trees. The proof is outside the scope of what I want to cover today, but it's understandable by a motivated undergrad. I encourage you to read Proofs from the Book, which contains many beautiful proofs with minimal prerequisites, including a proof of the matrix tree theorem. Kirchhoff's matrix tree theorem has inspired most of the research I have done, but this is not just because of what the theorem says, but also what the theorem doesn't say. When two sets are the same size, combinatorialists like to look for nice bijections between them. A bijection is a pairing between elements of one set and elements of another. For example, here is the set of first names and the set of last names of mathematicians who have won the Fields Medal in the last decade. Not only are these sets the same size, but there is a very natural bijection between them. We can associate each first name with the last name that combines to form an award winner. This bijection gives us a better understanding of how these two sets relate than just the fact that they're both the same size. On the other hand, while there are plenty of bijections between colors of the rainbow and dwarfs in Snow White, these bijections don't actually give us more information because it's just a coincidence that these two sets are the same size. It's actually quite difficult to define mathematically what it means for a bijection to be meaningful, and it's a topic I'm interested in exploring further in my research. But from a practical standpoint, you can generally judge what seems arbitrary and what seems meaningful. So now we return to the Sandpile group and spanning trees of a graph. It seems like the relationship can't be a pure coincidence, but if you read through the standard proof of the matrix tree theorem, it does not suggest a nice bijection between S of G and T of G. There's also the issue that S of G is a group, which means it has a very special identity element, whereas T of G doesn't have a group structure and often has no special spanning trees to associate with the identity. Of the spanning trees of our graph, for example, there isn't one that sticks out above the rest. Instead of defining a map between S of G and T of G, we'll define an action of S of G on T of G. This means that we will input a spanning tree and a sandpile element and output a new spanning tree. Now, the special identity element is no longer an issue, because if we act on a spanning tree by the identity, we just leave it alone. What properties would we like this map to have? Well, if we fix any spanning tree as the input, we can require that every sandpile input maps to a different spanning tree, and every spanning tree is mapped to by some sandpile element. A group action satisfying these two properties is called a free transitive action. A free transitive action from S of G to T of G is called a sandpile torsor. Essentially, a sandpile torsor is a bijection between S of G and T of G after we choose a distinguished spanning tree. So now we ask, are there any nice sandpile torsors? It's almost time for the most exciting part of the talk. To celebrate this fact, I have a new, more interesting graph. For technical reasons, to get a nice sandpile torsor, we need to specify an ordering of edges around each vertex. I'll just let them be clockwise. We also need to choose a vertex to put a red box around that we will call the sink. And now we're ready to go. We have a spanning tree on our graph with a sink, and we also put a blue dot on some vertex. Let's turn the edges into arrows called rotors, which point toward the sink. Now, the blue dot is going to go on a journey across the graph by repeatedly following two rules. First, it spins the rotor one position. Then, it slides across it. This continues until it reaches the sink. At this point, the arrows are erased and we have a new spanning tree. We now have some kind of action of blue dots on spanning trees. But what if I told you the blue dot was a chip in disguise? We are actually working with a chip configuration that puts one chip on the blue dot, a negative chip on the sink, and no chips anywhere else. But I know what you're probably thinking. What about divisors with more than one chip? Like this divisor, for example. Well, let's deal with one chip at a time and see what happens. It turns out you can let the chips move in whichever order you want and you still get the same result. These rotors might look very different in the middle of the algorithm, but once the chips all reach the sink, we will always get the same final spanning tree. See if you can prove why this is true. How can we use this idea to define an action of S of G on T of G? Well, every firing equivalence class has representatives that have a non-negative number of chips away from the sink. But how do we know which one to choose? As with the last result, it doesn't matter. A vertex firing is just like a rotor spinning all the way around. We now have defined a group action of S of G on T of G. First, we choose an appropriate representative. Then we direct the edges to get our rotors. Finally, we let the chips spin the rotors until they all reach the sink. We're not quite done yet, though. We have an action, but we don't yet know that it's a sandpile torsor. We still have to show that when we fix a spanning tree, this action gives a bijection between the sandpile group and spanning trees. Because the sets are the same size by the matrix tree theorem, we just need to show that for every pair of spanning trees, there's a sandpile element that sends the first to the second. Let's see if I can convince you this is possible by giving an example on our old graph. Suppose that we want to send the tree on the left to the tree on the right. First, we orient the rotors toward the sink. Then, for each non-sink vertex, we check how much the associated rotor needs to move. The bottom left rotor needs to move 2 positions, so we put a 2 on this vertex
and a -1 on the next two vertices the rotor will face. The top left rotor is already in the right spot, so we don't have to do anything. Finally, the top right rotor needs to move one position, so we put one chip on its vertex and -1 on the vertex this rotor faces next. Add the chips on each vertex and we have our S. There is one issue with this method, which is that we can end up with a negative number of chips on a vertex other than the sink. However, this turns out not to be a problem. I encourage you to fill in the details and show why this method really can be used in general. Thus, we have an algorithm to get a sandpile torsor on every graph. This is called the rotor-routing sandpile torsor algorithm. Hi, thanks for listening. I hope you enjoyed the talk. There's so much I didn't get a chance to cover. For example, if you Google Sandpile Group, you're going to get a bunch of beautiful pictures that look like this. And it's not too hard to say what's going on here. It's just it didn't really fit in with what I wanted to talk about. There's also plenty of great resources to learn more about chip firing, more as of recently. There's these two very new textbooks, Mathematics of Chip Firing by Carly Clivens, who's my advisor. And then there's this Divisors and Sandpiles by Scott Corey and Dave Perkinson. Both approachable by undergrads. Definitely check it out if you're interested. And even beyond the textbooks, some of these papers are very readable. And the first papers I ever read were on this subject. So I have here a printout of the first paper I ever read. It's called Chip Firing and Rotor-Routing on Directed Graphs. And a lot of the results that are in this presentation, I first learned about from this paper. So I'll put the link in the description. Another paper I highly recommend that you're just ready to learn about now is this one by Chan, Church, and Grachow that asks the question of what happens if you switch the sink? Do you get the same sandpile torsor? It ends up, the answer is very interesting. It depends on whether or not the graph is planar. So you can read that and learn about that fact. I'll also put the link in the description. And then if you really want to make me feel special, you can feel free to read my thesis. It's on my website, and it's kind of long and more aimed at grad students than undergrads, but I do try to put all of the necessary background in there for the most part. So check that out. Let me know what you think. Comment on the video, and have a great day.